Bonsoir, mesdames et messieurs, et bienvenue à cette troisième conférence du cycle « Les secrets du soleil » du Colloque Wright. Quelques petites informations pratiques. Vous avez reçu des feuillets sur lesquels vous êtes invités à écrire vos questions. Les hôtesses ramasseront ces feuillets à la fin de la conférence du professeur Jerry Meal, et ces questions seront ensuite posées aux conférenciers à la fin de cette manifestation. Il y aura une petite pause de 5 minutes entre la fin de la conférence et la réponse aux questions. Donc que ceux qui désirent entendre les réponses aux questions restent bien sûr dans la salle. Une autre information, comme vous le savez, le Colloque Wright cette année vous propose un spectacle, son et lumière, que vous pouvez voir tous les soirs à 17h45, 19h et 20h30, et ceci jusqu'au 23 novembre. Les deux premières conférences de ce cycle étaient focalisées sur le Soleil proprement dit et ont été données par des astrophysiciens et des physiciens. Les deux prochaines vont s'intéresser aux liens qui existent entre le Soleil et notre petite planète bleue. Et en fait, vont parler évidemment du Soleil comme source d'énergie et comme aussi source potentielle d'influence de notre climat. Je vais maintenant passer la parole au professeur Martin Beniston, qui est climatologue et qui est le directeur de l'Institut des sciences de l'environnement, pour présenter le professeur Jerry Meal.
Merci beaucoup, mesdames et messieurs. It's a great pleasure and an honor to introduce the speaker of this evening. Gerald, or Jerry Meal, was born in 1951 in Colorado and undertook his higher education at the University of Colorado in atmospheric science for his bachelor's degree and in climate dynamics for his master's and doctorate degrees. He is currently senior scientist at the Climate and Global Dynamics Division at the world-renowned National Center for Atmospheric Research, NCAR, in Boulder, Colorado, a research institution with which he has been closely involved since the late 1970s. His research covers a wide range of topics and interests, with numerical modeling of the climate system a central focus of his work. He has contributed to improving the understanding of ocean-atmosphere interactions, decadal scale climate variability, and more generically, the predictability of climate. In this context, since 2011, he is Vice Chair of the National Research Council Board on Atmospheric Sciences and Climate of the National Academy of Science. Jerry Meal has been extremely active in shaping many programs aimed at furthering our understanding of the complexities of the climate system. Among these many committees, I mention here the TOGA Core Working Group on Tropical Ocean-Atmosphere Interactions to better understand elements such as El Niño Southern Oscillation, CLIVAR, the Climate Variability and Predictability Initiative of the World Climate Research Program, whose secretariat is at the World Meteorological Organization here in Geneva, and has chaired or been member of numerous national and international committees set up to promote numerical modeling of the atmosphere and climate, such as the NCAR Community Earth System Model. Jerry has an impressive publications record with over 240 peer-reviewed papers that he has authored or co-authored in international scientific literature. I am extrapolating here, Jerry, since the only CV I was provided for this evening dates back to 2012. In 2007, he was finalist for the NCAR Outstanding Publication Award, and in 2009 received the Jules Charney Award, one of the most prestigious distinctions of the American Meteorological Society. Since 2005, he has been associate editor of the Journal of Climate, one of the leading journals in the field. I could, of course, continue for quite some moments here. After all, Jerry Meal's CV is almost 40 pages long, but we do want to hear Jerry's talk, so I will close here with a final excerpt from his CV that brings testimony to his international stature. He has been involved from the very beginning in the activities of the IPCC, the Intergovernmental Panel on Climate Change, as a contributing author in the first assessment report back in 1990, and subsequently as convening lead author in all reports up to the most recent fifth assessment report, published just 1 year ago. As you probably know, the IPCC was awarded the Nobel Peace Prize in 2007. Jerry, I'm looking really forward to your talk, so may I now ask you to come to the podium. Thank you very much.
Well, thank you very much, Martin, for that very kind introduction. And I also wanted to thank the Dudley Wright Foundation for inviting me to give this talk. It's really a great honor to be a part of this Wright Science Colloquium. And it's been really interesting this week hearing all the really fascinating science talks and all the exciting science that's been discussed. And as Martin mentioned, because I'm a climate scientist, I have to say something about the weather. People have been apologizing all week for the kind of not really great Geneva weather. And I said to him, well, you know, this week in Boulder, Colorado, where I live, we've had our first really severe cold snap of the season. And before I came over here tonight, I checked the temperature in Boulder, and it was minus 17 centigrade. Minus 17 centigrade, and there's about 15 centimeters of snow on the ground. So 10 degrees centigrade and a few clouds and a little rain actually is a better alternative, I think, to what's going on in Boulder right now. So I'm going to talk about the sun and the Earth's climate, and I put in parentheses here a detective story. I really don't need to put that on here, I think, because the talks you've heard this week already, you understand that science is really about being a detective. Scientists are detectives, and they're always trying to figure out what's going on. They see something they don't understand, and they try to come up with ways to explain it. But this particular saga, it is actually, of this history of the connection between solar variability and Earth's climate has kind of an interesting, actually kind of a tortured history, because if I was giving this talk 30 years ago, my colleagues would have told me, don't do it. You know, anything associated, people that talk about the connections between Earth's climate and the solar variability are labeled quacks. They're labeled to be, you know, kind of deranged or something, because solar connections to Earth's climate really fell into disrepute for about 100 years. It's only been in the last 30 years that we've made significant discoveries where we've actually been able to document and do actually some really good science to make these connections between the sun and Earth's climate and make it a really an interesting, exciting field of science right now. Just to give you an indication of what we were up against 30 years ago, this is a quote from Hubert Lamb, who was a very famous climate scientist in the UK. And he was talking in the mid-90s, shortly before he passed away, and he said he was looking back on the history of kind of looking at the connections between solar variability and Earth's climate. And he said, for a young climate researcher to entertain any statement of sun-weather relationships was to brand oneself a crank. I'm not quite sure what the French translation for that particular word may be, but you kind of get the idea that it was really not it was kind of a disreputable area of science. So I'm going to try to show you how far we've come in the last 30 years and to give you an indication of kind of some of the latest things we're looking at in this field. One of the reasons this has kind of become more relevant lately is that almost anything you think about, people always think that it's causing the climate to change. And this is just one example quoted. A scientist who I will not name was quoted on the BBC last year as saying, solar activity is influencing global climate, causing the world to get warmer. So that leads you, of course, to ask the question, is global warming caused by the sun or by us? And so we're going to return to this as we go through this. So just kind of give you a background of how the sun influences climate. Obviously, we wouldn't be here without the sun. The sun is a source of energy that powers everything on the Earth, makes the planet habitable. And in fact, weather systems exist because of the differential heating between the sun being more intense and more directly overhead in the tropics and having less intensity in the high latitudes. So as the tropics heat up, weather systems form to move that heat out of the tropics and get it into the higher latitudes where the heat can be radiated more effectively to space. So the sun is a source of weather, it's a source of climate, it makes the place habitable, and that's kind of the first order effect that it has on our system. But then when you think about how ways that the sun can affect Earth's climate, the first category is how the Earth's orbit and its tilt is oriented in relation to the sun. And probably everybody learned this in school, but the first most obvious thing is the seasonal cycle. And this, of course, is due to the tilt of the Earth's axis. As it goes around the sun, when the Earth's axis is tilted closer to the sun in the northern hemisphere, the sun's more intense in the summer and we get summer. when the Earth orbits around to the other side and the tilt is oriented away from the sun for the northern hemisphere, the sunlight's less intense and we get winter. So you get these really dramatic seasonal changes. This is just due to the fact that the Earth has this tilt, and as it orbits around the sun, you get the seasons. And in fact, when you look at, for example, in Geneva, the sunlight's about 5 times more intense in the summer than winters. That's quite a big difference in the intensity of solar energy hitting the Earth, and this produces these really drastic seasonal cycle changes as you go through the seasons. Another way that the Earth's orientation to the sun produces interesting phenomena is something called Milankovitch cycles. And this guy Milankovitch in the early 1900s figured out and did these calculations that the Earth's orbit is not perfectly elliptical. It's actually goes through various changes, and sometimes it's very elliptical as it goes around the sun, and sometimes it's nearly circular. And as it goes through these cycles, it also, that's the eccentricity, it is about a 100,000 year cycle. Precession is the kind of the direction of the Earth's tilt in relation to the Earth's orbit around the sun. And the obliquity is kind of how much it's tilted. So sometimes it's tilted more than it is now, sometimes it's tilted less than it is now. So all these things are going on. The Earth's axis is wobbling, it's changing the shape of its orbit around the sun. And these things produce differences in the intensity of just the solar radiation that reaches the Earth on the order of about 20%. So during the last ice age, which was about 22,000 years ago, the sunlight was about 20% less intense due to these factors involving the orbit. And we got this kind of situation here. This is just a depiction of the ice sheets going way down here into North America, down here into Europe and Northern Asia, South America, even parts of Australia. And so there was a lot of these ice sheets that formed, and the last peak to the last ice age was 22,000 years ago. And these are really highly correlated to these changes in the Earth's orbit. So those are just two ways. The seasonal cycle and the ice ages are ways where just changes in the Earth's orbit and tilt can give you some differences in the intensity of the solar radiation without the sun actually changing its output at all. But of course, there are other things going on in the sun that actually change the amount of energy that comes out of the sun. And the most well-known or well-documented is this thing called the 11-year sunspot cycle. And this actually, sunspots have been observed for hundreds of years. There's at least one documented instance in China in 400 BC. They were noticing that there were spots on the sun. And so this has been a fairly well-known aspect of the sun for many hundreds of years. And what ends up happening is that, I'm going to talk about this a little later, but there's somewhat greater energy that comes out of the sun when you have a lot of sunspots, which is somewhat counterintuitive because you think a spot on the sun is a dark spot and you should have less energy coming out of the sun, but actually the edges around the spots are these so-called faculae, and they actually are much more, they put out even more energy than the spot is taking away. So in total, when you have more sunspots, you have more energy reaching the Earth, but it's a very small fluctuation. So we talked about the seasonal cycles, like 5 times in summer than winter. Ice ages are about 20% between ice ages and interglacials. The solar variability coming out of these sunspot cycles is less than 1%. So it's a very small variation. But there's a really interesting history that goes along with sunspots, and because they're fairly easy to observe, people have been observing them for a long time, and one scientific controversy, and of course there's never controversies in science, right? But this particular controversy was an interesting one, kind of typical of two scientists kind of arguing, but it had a religious angle to it because this is in the 1600s, Christoph Scheiner was making drawings. He was actually drawing sunspots he was observing moving across the face of the sun, but the religious dogma at the time was that God created everything perfectly, and the sun was a perfect thing. And if there were blemishes on it, like sunspots, then that didn't really fit with their perception of how the creation actually worked. So his idea was, it can't be spots on the sun, it can't be blemishes, it must be shadows from something, maybe some other planets or something going by the face of the sun that was just causing a shadow. The sun itself was perfect. Galileo was, at the same time, was looking at sunspots, and he was arguing, no, they've got to be on the face of the sun. And this is just another way that Galileo got himself in trouble with the church, but this is kind of one thing that he was right about in terms of the sun. The spots were actually on the surface of the sun. So then we come along, and as we kind of come up to the end of the 19th century, we were starting to get enough weather observations that people have been collecting from weather stations and other things that we had a long enough record that you could actually look at relationships between weather events and the 11-year sunspot cycle. And so scientists were looking through these data, and they were always finding correlations with various things in the 11-year sunspot cycle. And they kept announcing success. They said, oh, great, we've got a great predictive tool. We can just look at the 11-year sunspot cycle, and then we can predict exactly what the weather's going to be like, 10 or maybe 20 years in advance. But the catch, and this was a big catch that actually plagued this area of research, which actually made it kind of disreputable, is that there was never a plausible mechanism which physically connected the sunspot cycle with climate. In other words, you could see these associations, but correlation is not causality. And so until you have an actual physical mechanism where you can actually say what's happening, all these things were viewed as pure speculation. But there were some heavy hitters that were getting involved with this, at least in the US. This guy, Ellsworth Huntington at Yale, he was saying high sunspot numbers mean storminess and rain in some parts of the world. Now we're in the early 20th century. This guy, Charles Greeley Abbott, who was a well-known astrophysicist, he was at the Smithsonian, and he said there's a plain correlation between the sunspot cycle and cycles of temperature on Earth. But even Abbott's measurements, and he was actually trying to measure the differences in solar output with the sunspot cycle, showed that this varied less than 1%. And so people were just saying, well, how could this possibly, this really tiny fluctuation in the output of the sun cause changes or affect the Earth's weather? So we get into the 1920s, and more of these studies are being done, more of these correlations are found with various phenomena. And you had some very well-respected scientists that got into this business, and they were making various predictions. And then, of course, amateurs were kind of doing it and getting their names in the paper, and they were announcing correlations and said, okay, we know enough about these correlations that we can make predictions, but of course, every prediction failed. And this slowly fell into disrepute. And scientists that were kind of looking at this were viewed with great suspicion because, again, there was never any actual mechanism to connect these phenomena. So kind of in the background, in the late 1800s, there was this guy, Walter Maunder, and he noted that this well-known lack of sunspots, and this was a very well-known thing because about the time everybody was recording sunspots, they actually disappeared for about 60 years in the 1600s and 1700s. And he noted that he was studying various European writings and looking back at old paintings and things like that from the 16 and 1700s. And this period, which he called the Little Ice Age, which was a very cold period in various parts of Europe and other parts of the Northern Hemisphere in the 16 and 1700s, seemed to correspond to kind of right in the middle of this lack of sunspots that occurred about the same time. And he said, well, maybe fewer sunspots produce these colder winters that were characteristic of the Little Ice Age. So that was an interesting little tidbit. And fast forward to the 1970s, and a scientist at my institution, the National Center for Atmospheric Research, NCAR, named Jack Eddy, he was very interested in this Hans Suess, who had actually kind of resurrected Maunder's work from the 1890s. And Jack Eddy actually was bold enough to say that when you look at the record of sunspots coming along here from 1600, and here's this lack of sunspots, which Jack Eddy named the Maunder minimum after Maunder, who made this connection to the Little Ice Age. He said that the Maunder minimum, this lack of sunspots here, was a major contributor to the Little Ice Age. These very cold winters in Europe that actually lasted for a couple hundred years. And this Maunder minimum was just part of this, but he thought this was a major contributor to this Little Ice Age. But he admitted he still didn't have a mechanism to physically connect this. So this was kind of poo-pooed, and even at NCAR, the other scientists were kind of thinking that he was way out on a limb, and what was he thinking getting into this and trying to make these connections. Another connection to my institution was Walter Roberts, and he was the first director of NCAR, and he was a solar physicist, and he was at Harvard, and he was going to drive to Colorado from Harvard. Colorado's in the middle of the country, and he was going to go up in the mountains and set up a solar observatory. And he was doing this drive in the late 1930s, and as he drove through the center part of the country, he was seeing the remnants, the ravages of the Dust Bowl drought that was a really terrifically bad drought in the middle part of the U.S. in the 1930s. Corresponded to a peak in the 11-year sunspot cycle. And he was intrigued that there's got to be some connection. And he said that he wanted to look at the effects of drought on the high plains, but he said, we have no direct proof of the mechanism. So this is 1978 now. And he says, we have some radical speculations about how it might work. We are still left with an unresolved mystery. So that's kind of where things were. But one of the reasons he set up the National Center for Atmospheric Research was to try to get climate scientists and solar physicists together to try to sort this out. And that was kind of the original motivation for that institution. So now we come into kind of the modern era. So we've got, the stage is kind of set, even though people that are looking at this are still viewed with some suspicion. And it came along, this guy here, Harry Van Loon and Karen Lubitska. Harry Van Loon was an NCAR scientist. Karen was a scientist at the Free University in Berlin. And Harry Van Loon was actually one of my thesis advisors. And he was a very famous, well-known scientist for studying tropical Pacific climate variability. El Nino and Southern Oscillation. El Nino and Southern Oscillation are the biggest year-to-year fluctuations that we know of in the climate system. And so he'd done this very nice work looking at these phenomena in the Pacific. And in the late 80s, he all of a sudden veered off into this solar work. And I was talking to him and I said, Harry, you're out of your mind? This is a crazy thing to do. You're well known for your work on El Nino, and this solar stuff is really kind of flaky. And he goes, no, there's something to it. He says, there's got to be something to this. And he says, we just have to look at it in the right way. And so he started working with Karen Lubitska, and they actually started looking at some weather data that was becoming more widely available. For example, in this paper in 1994, they were looking at weather balloon data. So they were trying to look through the whole depth of the lower part of the atmosphere to look at connections to the sunspot cycle. And right before this, it was pinned down that these faculi are actually producing more energy. So the peaks in the sunspot cycle were actually producing more energy, and that was measured more accurately about this time. So we had better measurements of the solar output. And he was looking at things like the vertical motion in the tropics might be stronger at the peaks of the solar cycle. The mechanism of the solar effect must include year-to-year variability of the tropical circulation on the time scale of the sunspot cycle. And he also noted that there seemed to be cooler equatorial Pacific Ocean surface temperatures during peaks in this 11-year solar cycle. So now he was trying to pin down regional things that may connect to a mechanism, which was a very important kind of thing to do. And finally, we actually had a breakthrough that occurred in 1996. Joanna Haig from Imperial College in London described and actually modeled this so-called top-down mechanism. So for the first time, she proposed a mechanism, she proposed how it would work, and had a climate model where she could demonstrate how it worked. And this was a very important kind of thing in this kind of progression, because this signified for the first time a quantifiable mechanism that connected solar, the 11-year sunspot cycle, and Earth's variability. So how this works, I'm just going to go through this relatively quickly just to give you an idea that it's not a simple kind of a thing. But increased solar, peaks the 11-year sunspot cycle, means you have all the radiation that comes from the sun includes many wavelengths, and the ultraviolet in particular interacts very critically with ozone in the stratosphere. In other words, ozone absorbs ultraviolet radiation from the sun. And we have a little bit more of this coming in at peaks in the cycle. You have a little bit more absorption of that ultraviolet by the ozone. The ozone heats up a little bit. That warms the stratosphere. And you get one little feedback coming in because the ozone likes warmer temperatures. You actually create more ozone when the stratosphere warms up a little bit. So that's already a little bit of an amplifying feedback. But what happens when you start heating up the stratosphere is you start changing the temperature structure as well as the winds in the stratosphere, and waves that are coming out of the lower parts of the atmosphere from the troposphere that come up into the stratosphere get refracted in various ways and are kind of bent back down into the troposphere. And this changes in winds and temperature in the stratosphere because of this ozone interaction with the ultraviolet from the solar changes how energy is transported and changes the atmospheric circulation down where we live. There's two effects from this that she documented. One, stronger precipitation in the tropics, which kind of confirms what Harry Van Loon and Karen Labisca were talking about was important, and stronger west winds, a stronger polar vortex that rings the Arctic, and a positive phase is something called the North Atlantic Oscillation, which we'll talk about a little bit later. So after Joanna's paper, a lot of other people started modeling this, and this seemed to be the best candidate, and really the first tangible connection between the 11-year sunspot cycle and Earth's climate. But the key thing about this is climate models. And climate models were becoming well enough to use, or high enough quality to use for these purposes in the 90s. So it's worth saying a little bit about what a climate model is. It's basically a set of equations. You take these equations from physics and thermodynamics. The dynamical equations, if anybody took calculus, they're nonlinear partial differential equations, so you can integrate them forward in time and get things like the winds, pressure, temperature, and the physics. You can get rainfall and other kinds of things. So you have this set of equations, and the way you solve them is you divide up the globe into a latitude-longitude grid. And at each intersection of these latitude and longitude lines, each grid point, you solve all these equations everywhere on the surface, in maybe 60 levels going up into the atmosphere, maybe 60 levels going down in the ocean. You have another set of equations for ecological interactions and land surface processes over land, another set of equations for Arctic and Antarctic sea ice, and you run all these equations and you try to simulate this. This is a satellite photo of the Earth, and it's a very complicated system. And the thing that always amazes me is we can get anything out of these equations that looks like planet Earth. It's really pretty amazing. Because you look at this complexity, and here's North America and South America here, the Pacific. This line of kind of big thunderstorms going across here is something called the Intertropical Convergence Zone, or ITCZ, where the trade wind systems from each hemisphere converge in the tropics and provide vertical motion. When you have vertical motion in the tropics, you get more precipitation and more clouds, and you release more energy into the system. You can see that we have big storm systems in the mid-latitudes. These are big low-pressure systems with cold fronts coming out from them in both hemispheres. In the tropics, the winds are blowing from east to west. In the mid-latitudes, the storms are going from west to east. And you can see things like this. I think this picture was taken the day Hurricane Katrina actually hit New Orleans, but that's a big hurricane. Of course, you get these systems that are called typhoons and tropical cyclones in other parts of the world as well. So you see, this is a very complicated system, and we're trying to simulate all this with sets of equations. So let's just see how we can do. This is going to be an animation, hopefully it'll work, from one of our models at NCAR, just to give you a flavor of how you can simulate these weather systems just with these sets of equations. This is going to be from a typical August. So in August, and you can see these clouds and precipitation features, or the white features here. Here's North America and South America, Africa and Asia. Here's the Intertropical Convergence Zone, and another big convergence zone called the South Pacific Convergence Zone, which is another big feature of Pacific climate. The so-called ITCZ actually extends into the Atlantic. Since this is Northern Hemisphere summer, we're going to see a lot of rainfall over the Indian monsoon. This is the time of the rainfall maximum associated with the Indian monsoon. And you're going to see some typhoons forming over here in the Western Pacific, as well as these storms. And you can kind of see very faintly these big cold fronts coming out of these storms in the mid-latitudes. And they're going to be going from west to east. And the tropical flow is going to be going from east to west. So let's just see if we can run this. Okay. Now you can see these systems are going from east to west with the trade winds. You can see the mid-latitude systems are going from the other direction. Here's a typhoon that's going to come over here into Asia. Here's another one forming. You can see Indian monsoons getting a lot of rainfall here. Here's a big cold front. Here's another big storm going across the North Atlantic in the northern hemisphere here. So you can see these storms are kind of whipping along, going through the mid-latitude westerlies. Everything in the tropics here is going the other direction. And see, I just love watching this. Let's watch it one more time. So here's a big storm in the southern hemisphere, this big cold front coming down here. And since this is summer, the storms are a bit weaker in the northern hemisphere, but of course this is the time of year when you get more typhoons and hurricanes. We don't, in this sequence, don't have any hurricanes in the Atlantic, but we have a couple of them here in the Western Pacific. And you can see this monsoon circulation is producing a lot of rainfall in the Indian monsoon system. So this is all just being done by equations run in a supercomputer. So that gives you an idea of what, we have this capability, and now we can use climate models as a tool to try to figure out what's going on in the system. Of course, they have a lot of limitations, but you use them as tools to try to give you some insight. So the first thing we want to try to do, or one of the things we want to try to do, is let's try to simulate 20th century climate with one of these climate models. And I'm going to show this a couple different ways, but the first thing I'm just going to talk about was one of the things that related directly to this solar problem. This is a reconstruction of what's called total solar irradiance. This is the total amount of energy coming out of the sun. This is one of the input variables that goes into the climate model from 1880 up until roughly 2010. The light blue line is the 11-year sunspot cycle, and this is reconstructed from sunspot data. We don't actually have direct measurements of the total output of the sun's energy until the late 1970s, but we've taken those observations from the late 70s from satellites and gone back and recalibrated the sunspots that we observed, that we have sunspot counts from. And you have this reconstructed time evolution of the total solar output, and this blue line is some kind of smoother that's kind of run through there to give you an idea of the lower, the kind of the slow fluctuations. And one of the things you see right away is here from the 1900s up to mid-century, there seemed to be kind of a slow increase in the amount of radiation being put out by the sun. And since then, it's been either level or even falling off a little bit. But this early century increase in solar output, which is on the order of, it's between 3 and 4%, depending on how you measure it. And remember that the peak to trough values of the 11-year solar cycle on average are less than 1%. So this is a little bit more than the amplitude of the 11-year sunspot cycle. So it turned out that this small increase in total solar output on the order of 4% ended up having an effect on climate. And this is a kind of a complicated map, but I'm just going to show you a couple of features. This was one of the things that we were looking at. I was actually looking at this, and this was still when I was thinking Harry Van Loon was out of his mind for looking at this solar stuff. And I was looking at model output, and this is plots of precipitation from mid-century, or from early century to mid-century, the difference in precipitation, and temperature, surface temperature from early century to mid-century. And these are differences, but there's a lot of kind of blobs and colors, but here's South America, North America, Australia, so this is the Pacific. And remember, that was noted by these earlier modeling studies and by Harry Van Loon and Karen that we want to look for increases of precipitation in the Western Pacific and Eastern Indian Ocean in particular. These orange colors here are increases of precipitation occurring roughly in that area. And we also wanted to see a little bit of a cooler equatorial Pacific ocean surface temperatures during this time period. And these blue colors here show that we're getting really small but observable cooling of the Eastern equatorial Pacific during this kind of period where we had an increase of solar output from the early to mid-century. And the odd thing about this was when I looked at this, I said this should not be happening because at this time there was only one mechanism, the top-down mechanism. It depended on stratospheric ozone. It depended on stratospheric dynamics. This model that we were using didn't have much in terms of realistic stratospheric dynamics, and it had no ozone chemistry. So it did not have the top-down mechanism. But we were still getting this response that had been seen in the observations that people thought were important. So what's going on? So after quite a while of trying to figure this out, we came up with another mechanism, the so-called bottom-up mechanism. And the way this works is like this. And I'm going to try to walk you through this, and I may not get all of it, but the idea is that remember that picture I showed you of the Pacific from the satellite map earlier, and you saw the intertropical convergence zone, those band of thunderstorms going across the Pacific. There weren't many clouds to the north and south of that big band of thunderstorms. I said that's where the trade winds converge. Well, there's relatively cloud-free regions. If you've ever been to Hawaii, you know that there's not a whole lot of clouds in Hawaii because that's kind of in the area of the trade winds. The intertropical convergence zone is south of Hawaii. You see the same thing south of the equator. So the idea is that the sun can only affect the surface where it gets to the surface. So if there's clouds, the sunlight's reflected back to space, and it doesn't really have any effect on Earth's climate. If there's cloud-free regions, the sun gets all the way to the surface, and it can affect the surface. So when the sun is most directly overhead in the tropics and subtropics, say between 30 north and 30 south latitude, and in these big areas of the Pacific Ocean where there's not many clouds, you say, well, those are the areas where this small increase of solar output can actually get to the surface and affect the surface. And when that little bit of increase of solar during the peak of the 11-year sunspot cycle gets to the surface, it warms up the ocean just a little bit. That little bit of ocean warming evaporates a little more water, so you have a little more water vapor in the surface layer, and that's right where the trade winds are blowing. So the trade winds pick up this additional moisture, carry it into these big convergence zones where you have these big thunderstorms and big vertical motion, and intensifies that circulation. So you actually get stronger thunderstorms, these big convective systems in the intertropical convergence zone and in the western Pacific and eastern Indian Ocean. And you get this vertical motion, which characterizes increased precipitation, and all this air is kind of pulled up along with the convection as the clouds form, and then the rain comes out. And this mass of air that's going up, it has to come down somewhere, so it actually spreads out as it gets into the upper part of the atmosphere and descends. And it comes back down in some areas, back into the areas of the eastern Pacific and the subtropics. This is called the Walker circulation, and it's a very well-known aspect of Pacific climate that's usually associated with El Nino, but this is the same set of mechanisms, but kind of kicked off by actually increased solar. So descending air means you're actually warming the air as it descends, and you're actually dissolving clouds. You're actually getting fewer clouds. So now you're getting an amplifying feedback. Just due to the changes in the atmospheric circulation, you're getting fewer clouds, even more sun gets to the surface, you get a little more evaporation, and the whole thing intensifies. And so you can magnify a very small change in solar input into the system through these sets of air-sea coupled interactions and large-scale circulation. And the trade winds get stronger because they're now getting pulled into this stronger vertical motion. And as the trade winds are blowing along the equator, they're pushing the warm surface water to the west, and cooler water from the subsurface is coming to the surface. And that's what's producing that little band of cooler ocean temperatures in the eastern equatorial Pacific. So we thought, well, this was kind of an interesting new mechanism, and it seemed to help explain some of the things we were seeing in the models. But we still needed to pin this down, so this is kind of more science than you want to look at. But I just wanted to show this because this was a set of experiments we did where just to demonstrate what you can do with a climate model. You can turn things on and off, and you can do kind of controlled experiments to try to test these mechanisms. So for peaks of the 11-year sunspot cycle, these are the observations of surface temperature at the top and observed precipitation. The reds and oranges are greater precipitation during the peaks in the 11-year sunspot cycle. Here's this band of cooler equatorial Pacific SSTs here. Here's North America and South America again. This is the Pacific. If you take a version of the model and you take out the stratospheric processes, you don't have ozone chemistry and you don't have stratospheric dynamics, you're just left with the bottom-up mechanism. You're left with kind of a weak response compared to the observations. You still get this little cooling in the equatorial Pacific. These orange colors here are a little bit of enhanced precipitation in the western Pacific, but it's trying to do it, but it's not very strong. If you take another version of the model and you just have the top-down mechanism, and you do this by shutting off the coupling with the oceans. So now you have no air-sea coupling. Everything's happening in the atmosphere, so your ozone chemistry is working and everything else. Again, just with the top-down mechanism only, it's trying to produce this enhanced precipitation. These orange colors here are greater precipitation in this western Pacific, eastern Indian Ocean area that we thought was important, a little bit in the ITCZ here. But if you have a version of the model, you include both these mechanisms, you can see these colors are a lot darker, so that means you're getting a much stronger signal. So these two mechanisms are actually working in the same direction, kind of reinforcing each other, and they're both amplifying this very small fluctuation in solar radiance coming out of the sun. Now you're getting big, relatively large changes. They're approaching the observed magnitudes here in enhanced precipitation, and you see that this little band of cold water is stronger than it was here and closer to what we see in the observations. So that's just a way you can use a climate model to demonstrate these mechanisms and give you some insight into what's going on in these processes. Okay, so we talked a lot about the Pacific. So these regional effects seem to come out in the Pacific. Is anything happening anywhere else? The answer is yes, the North Atlantic. And just a quick result here. This is just to show that through this top-down mechanism I talked about, it strengthened the westerly winds around the Arctic and gave you a positive phase of what's called the North Atlantic Oscillation. That means for people who live here, milder winters when it's in the positive phase. When it's in the positive phase, if you're looking down from the North Pole, here's North America, Europe, Africa, and Asia. Here's the North Pole. These are sea level pressure changes for peaks in the 11-year sunspot cycle, and you can see there's lower sea level pressure over the Arctic, higher sea level pressure in the North Pacific and North Atlantic. This means the west winds are stronger. You're bringing in storms from lower latitudes. You don't get the real strong Siberian flow coming in from the east, which gives you very cold winters here. So you get mild winters, and this is from the observations, and this is from just one of many model simulations that shows basically the same thing. This opposition is sign between these sea level pressure anomalies over the Arctic versus those just to the south. Again, here's Europe right here. Just a note on this paper, you can see Van Loon. Harry Van Loon is now 88 years old. He published this, we think this is his last lead author paper. He published it earlier this year, and I think he's now going to call it quits. But his last paper actually still was dealing with this connection between solar variability and Earth's climate. Are there any other mechanisms? Well, as luck would have it, you're actually looking at this right here at CERN. This is a picture I took this morning. We got a really great tour of the cloud experiment out there. And this is this galactic cosmic ray mechanism. And the way this goes is that during peaks in the 11-year sunspot cycle, the solar magnetic field is stronger. So a stronger solar magnetic field that envelops the Earth protects it from incoming galactic cosmic rays that are these high-energy particles that are coming in from outer space. And they deflect the galactic cosmic rays away from the Earth. And the idea is that the galactic cosmic rays, as they come into the Earth's atmosphere, they can produce, through various collisions and other processes, they can produce little cloud condensation nuclei, or the seeds that form cloud droplets. And so when you have more, the theory is, if you have more galactic cosmic rays, you have more seeds for clouds, and you have more clouds. If you have fewer galactic cosmic rays, you have fewer clouds, more sun can get in. So when you have a strong solar magnetic field, the galactic cosmic rays are deflected away from the Earth. You get fewer cloud nuclei, fewer clouds, and a warmer climate at peaks in the 11-year solar cycle. So they're studying this mechanism out there at CERN, and stay tuned for results. It's a really interesting experiment. So we've already got two mechanisms we've identified that work in observations. We've modeled them. This is a third candidate that may actually also contribute, which would be an interesting thing. So you can see how we've evolved from even the 1980s, where this kind of area of science was disreputable, into really some kind of interesting science that's going on now. Okay, so back to this question we asked at the very beginning. The unnamed scientist who was quoted as the sun is causing global warming. So does the sun have anything to do with recent global warming? There's really a one-word answer to this: no. The reason I can say that is by just looking at a plot like this. This inset here is the best record, is the record we have of actual measurements from satellite of the total radiance of the sun, the total energy coming out of the sun. Here's the sunspots, the sunspot count going along here as observed. And you can see that peaks of the sunspot cycle are associated with peaks in the total output of energy from the sun, which confirms very nicely earlier measurements as well. So if you line up these measurements, which have been made since the late 1970s up until at least present, you can see that there's no trend in the energy coming out of the sun. If anything, it's going down a little bit. The peaks are successively a little bit lower as we're going along in these solar cycles. But during the same time period, since the late 70s, the global average temperatures, which is these lines up here, have been going up quite a bit. And obviously, it can't be the sun, because the sun has no trend. There's something else going on. So that's kind of one fairly obvious way of looking at this. But we think that the differences in solar output did actually affect parts of the record of temperatures in the 20th century. And I said a little bit before about this pattern that we noticed when we were looking at changes in the early part of the century, that we saw these patterns of cooler Pacific, equatorial Pacific sea surface temperatures and somewhat enhanced precipitation in the Western Pacific. But we can actually try to quantify this a little bit better on global scales by doing, again, sets of climate experiments. And again, using the climate model as a tool to help us try to understand what's going on in the system. So what we're trying to understand is this record. This is a record of globally averaged surface air temperatures in relation to a period here in the early 1900s. And you can see there's a lot of ups and downs, year-to-year variability, which are random fluctuations of the system. A lot of them are associated with El Nino and La Nina events in the Pacific. But when you look at these slower fluctuations, if you mentally draw a smooth line through this, you can see that there was this increase in the early part of the century, and it flattened out for the middle part of the century, and then it increased for a while. And it's actually been flat since about the year 2000, which is kind of another interesting part of the story I'm not going to talk about tonight. But what we're going to look at is this early century warming, because we think CO2, we started measuring CO2 directly in the 1950s, and it's been increasing ever since. But we have other bits of evidence that indicate that CO2 is increasing steadily since when we started burning coal, oil, and natural gas in the 1800s. So CO2 is increasing during this whole time period. But its increases weren't huge in the early part of the century. They keep getting bigger and bigger as we get later in the century. So let's use the climate model as a tool to see if we can kind of pull apart or deconstruct what happened in the 20th century here. So now this is using the climate model where we're just putting in the natural factors that have affected climate. The natural factors, the two biggest ones are volcanoes, volcanic eruptions, and solar variability. So remember that reconstruction I showed where we showed the solar irradiance was kind of increasing by about 4% in the early part of the century and then flattened off after that. If there's a big, especially a big tropical volcanic eruption, it spews up a lot of dust and soot up into the stratosphere. It reflects sunlight for a few years until it falls out. And volcanic eruptions tend to be a cooling effect on the climate. So this is now, you can imagine this line here, this blue line is the average of 5 runs with the model. We run the model more than once to give an idea of the spread among the model simulations, and that's this shading here. So that gives an idea of the uncertainty in what the model is calculating. And you can imagine that these temperatures here, this temperature record going from the late 1800s up until about 2000, is what would have happened on the planet if there would have been no humans. So there's no human effects here. And you see that there's this little bit of warming that occurred in the early part of the century. And then really it's been flat or even decreasing a little bit ever since. So this is evidence for two things. One is that there was this little bit of increase in solar output in the early part of the century that contributed to this. We also didn't have many volcanic eruptions then. So those two things we think are the main contributors to this early century warming. But okay, but what about this kind of late century disagreement here? Well, we can then go back to the model and add in the human-produced factors like carbon dioxide from the burning of coal, oil, and natural gas. And now we have the natural plus the human-produced, and you can see we're still getting this early century warming because we got that just from the natural, and now we're getting this late century warming when we've added in the greenhouse gases. So this is kind of an area of climate science called climate change detection and attribution. So you see if you can detect a change in the climate, and if you think you have a big change in the climate like this, can you attribute it to something? And this is one of the ways you can attribute basically cause and effect. And you can see that almost all this warming is due to human factors. So the question is, when you look back in time, have we ever seen anything like this happen before? And the answer is not really. And we know this because we have measurements from ice cores. Especially from Antarctica, they're the best ice cores. And we have a record going back to 800,000 years before present. And what happens in ice, on the ice caps in Greenland and Antarctica is as the snow falls and it kind of gets compressed, as it compresses into ice, it traps little air bubbles. And these little air bubbles are like little samples of air from when that ice forms. And so as the layers of ice build up, as you get successively deeper, you get older and older ice, and the air is still preserved in these bubbles. So when you do a core down through the depth of the ice, you pull it up and you can sample the air and see what was in those little bubbles of air and analyze the constituents. And that's how you can get these really great records of carbon dioxide going all the way back 800,000 years. These ups and downs are associated with the Milankovitch cycles. Remember, those were the ones, the changes in the Earth's orbit and its tilt, producing the ice ages. You can see the last ice age here was 20,000 years ago. We had low CO2 and low temperature. This is another way we can get temperature out of these ice core data. And you can see that the temperature is going up and down with the carbon dioxide, but it's actually leading it a little bit. And the reason is that this is the way that the system used to work. It used to be that the Milankovitch cycles would change the intensity of sunlight. You'd start warming the system up. Warmer water releases CO2 into the air. The CO2 in the air warms the system even more, makes the water even warmer, and you get that feedback loop going on between the water temperature and the CO2 in the air. And so that's how climate used to vary and produce ice ages. But we're forcing the system in a new way. And you can see that just in the last 100 years, CO2 was never above about 280 parts per million. It's now about 400 parts per million. That's just happened in 100 years. So this is really the biggest CO2 amount we've seen in at least the last 800,000 years, and perhaps even longer than that. Well, what about the future? So can the sun save us from global warming? What if there was what if the sunspots went away again, like they did in the 16 and 1700s? What if there was another Maunder minimum that happened? And because solar physicists don't understand really why we have an 11-year sunspot cycle, and they certainly don't understand why the sunspots went away during the Maunder minimum, we could have another Maunder minimum that could start in the next few years, and we wouldn't be able to predict it. We'd just see it happening, and we'd be in the middle of it. So there was a lot of great art produced during the Little Ice Age, and this is one, ice skating on the Thames River near London. See, these people are skating on the Thames River. Glaciers advanced in the Alps. It was really cold for quite a long time. And we think the Maunder minimum has something to do with it. So, okay, what if we had a Maunder minimum in the future? Maybe that could stop global warming for us. So let's try to use the model as a tool to test this. Again, here's the Maunder minimum. Lasted about 50 or 60 or 70 years or so. And then our science question, what would the climate response be to a possible future grand solar minimum? Say it started in 2020, just for the sake of argument. We're using a model that accounts for both mechanisms, the top-down and the bottom-up mechanism. And what we're going to do is we're going to put in a Maunder minimum starting in 2020 and running through about 2050 with 0 sunspots and drop the solar energy during that time period. Well, this is what happens. So the orange lines here are the kind of standard model kind of running. This is just showing globally average temperatures starting here in 1950 and going up through 2100. And you can see the orange lines, temperatures increase steadily because in this scenario, we're actually having a steady increase of greenhouse gases, ongoing burning of fossil fuels. We're not really doing anything about the problem. Our Maunder minimum that we put in the model starts right here in 2020, and you can see the temperatures cool off right away, but then they kind of just parallel what would have happened without the Maunder minimum. So what you would have liked to have seen was just this flatten out. You know, if you're thinking that a Maunder minimum is going to stop global warming, okay, it would just flatten out the temperatures. But no, it just kind of offsets it a little bit. And it still keeps warming up. And then when the Maunder minimums, or the future Maunder minimum stops, the temperatures kind of go back to where they were without the grand solar minimum anyway. So the conclusion from this is that a future grand solar minimum would slow down but not stop global warming. So we can't count on the sun to get us out of this problem. So just kind of one last thing to think about is that humans, us, not the sun, will have the biggest effect on future climate. And that may be kind of a depressing thought, but the good news about all this is that there's still time for us to decide the direction of future climate. And we can demonstrate this by this figure that appeared in the latest IPCC report. This is a synthesis of a lot of simulations from a lot of climate models from around the world. These are globally average surface air temperatures shown starting here in 1950, coming up through the early 2000s. And then we go off in 2 directions here. And these are 2 future emission scenarios that you say, okay, what if certain things happen? What if we kind of just continue business as usual? We continue burning fossil fuels like we are now. And you can see that the system continues to warm. These numbers here are the number of models that participated in this exercise from around the world. 39 models ran this experiment, 32 ran this experiment, 42 ran the 20th century experiment. So we've got a lot of models from a lot of different centers around the world doing this. And this is kind of the business as usual. The red line here in the middle is the average of all these model simulations, and the shading is the uncertainty, the range of the model responses. So you can see there's some range in the model responses depending on how they're put together, but they're giving a fairly consistent picture of this ongoing warming. But this scenario here is interesting because this scenario assumes that there's policy interventions to reduce emissions of greenhouse gases in various ways. And that means cutting emissions means maybe going to other alternative energy sources. It also could mean capturing CO2 in the air and trying to put it in the ground somewhere. So there's various ways that we know how to do this. If we did these things, you can see here that the temperatures stabilize out kind of mid-century and don't increase anymore. So this would be with a reduction in greenhouse gas emissions. And we know how to do this. We have the technologies right now, we can do it. It would require applications of these technologies at very large scales, but it is possible. It's not very plausible given the politics of this problem, but it is possible. We still can choose between this future and that one, and we know how to get to both these places, and it's still really up to us as to what we end up doing. So I guess just to kind of recap, I know I went through a lot of these things pretty quickly, so I just put these conclusions up here with some red highlights just to kind of review a little bit about what we talked about. I said that the sun can affect climate on Earth in two ways. This sun-Earth orientation, changes in the orbit and the tilt, produce the seasonal cycle as well as ice ages, and then actual variations in the energy output from the sun, the total amount of solar radiance, the amount of energy that comes out of the sun. And the most well-studied of those is the 11-year sunspot cycle, which produces changes in the output of solar output of less than about 1%. These sunspots have been observed for hundreds of years. People have been studying them for a long time. And the problem for 150 years of those studies were there was never a mechanism to tangibly link solar variability with the Earth's climate. But we finally got into a period where we had better climate models and better climate observations, and we were able to identify and model, reproduce in models, two mechanisms that demonstrate how you can amplify through these feedbacks, coupled feedbacks in the climate system. You can amplify this very tiny fluctuation in the amount of total energy from the sun into something measurable signals on these kind of 11-year cycles in the climate system, particularly in the Pacific and in the North Atlantic. And there's these two mechanisms, the top-down, the bottom-up mechanism, and there may be a third one involving cloud condensation nuclei and galactic cosmic rays that's still to be kind of pinned down. Global warming is not caused by the sun. We can say that definitively. And then can a future grand solar minimum or a modern minimum type period stop global warming? We did a study, and there's been a couple of other studies since then, that the solar minimum would not stop global warming, but just kind of slow it down for a while. So we can't count on the sun to get us out of this, but tried to leave you with a bit of hope that there's still time for us to affect the outcome of future climate change. And I would say that the longer we wait, the more difficult it will be to deal with. So I think it's in our best interest to try to think about doing something sooner rather than later. Thanks a lot.
Thank you very much, Jerry, for this fascinating insight into this highly complex system that we call the climate system. Mesdames et messieurs, nous allons prendre 5 minutes de pause pour les personnes qui aimeraient quitter l'auditoire avant la séance de questions-réponses. Merci beaucoup. So we'll have just a quick break here. May I ask the people who should be on the podium to take their seats on the podium, please? Voilà, merci beaucoup, mesdames et messieurs, pour votre patience. On va maintenant passer à la période de questions et réponses qui va durer environ 20 minutes. On va essayer d'arrêter la soirée autour de 8 heures au plus tard. So, thank you very much for being on the podium. And as you see, there's a whole range of questions here. I'm going to have to refuse some of them now. Thank you very much. Maybe I'll just kick off with... Since we've been very excited over the last couple of days with this highly technical landing of a little robot on the comet yesterday, geoengineering. I got a couple of questions on geoengineering. Is it possible to regulate climate through geoengineering? For example, are the artificial leaves invented by Daniel Nocera here? Could these be a means of reducing the CO2 effect on climate?
I could probably start out with this.
I think you need to.
I think it's on.
It's on, okay.
The most commonly proposed method for geoengineering, and by geoengineering we're talking about a technological fix to stabilize the climate, in other words, to kind of stop the warming. And the most common one is called solar radiation management, and this can be done in a couple of different ways. People noticed, and I mentioned, that when there's a big volcanic eruption, it spews a lot of dust and what we call aerosol particles up into the stratosphere, and that reflects sunlight for a couple of years until it all falls out. And it actually forms sulfate aerosol particles up in the stratosphere. So the idea is, well, what if we could just shoot rockets full of sulfur dioxide up into the stratosphere and have them explode, and then basically put all the sulfur dioxide up there where it reacts and forms sulfate aerosol particles, and those particles could then reflect sunlight. And if we just kept shooting rockets up there, or got this stuff up there somehow, we may be able to reflect enough sunlight to modify or moderate the climate due to the increase in greenhouse gases. Well, we've tried simulating this, and globally you can kind of stabilize the temperature, but the problem is, because you're putting this up in the tropics, these particles up in the tropics, you tend to get more of an effect in the tropics, more of a cooling effect in the tropics, but the high latitudes still kind of warm up a little bit more. So then you have all these ethical questions about, well, what's going to happen to tropical countries where the temperatures are a little cooler? That may have negative effects on what they're doing. You're still not going to solve the problem of the warming at the higher latitudes. And so it becomes a real kind of ethical minefield at some point, and this kind of global governance and who decides who's shooting these things in the stratosphere. And once you start, you can't stop, because if you stop shooting in the stratosphere, what's up there falls out, just like debris from a volcanic eruption. Then you see a big jump in the warming, because you've been burning fossil fuels the whole time, and CO2 is building up in the atmosphere. So that's one thing. The other thing is that because you're burning fossil fuels the whole time and CO2 is increasing in the air, you're forcing more CO2 into the ocean through ocean biogeochemistry, which makes the ocean more acidic. And so by changing the temperature, by just doing the solar radiation management, you're going to do nothing about ocean acidification, and we think that has some really bad effects on things like coral reefs. It can kill coral reefs. It can affect the little skeletons of these marine microorganisms that are at the bottom of the food chain with untold impacts. And so you're not going to solve that problem by this solar radiation management. So I think the science that's been done in this area has been more of, okay, what if we did this? What would the effects be in terms of just the physical science? We haven't even gotten into the ethical questions and who's going to administer this and decide how to do it and keep it going in perpetuity. So I think that's one aspect of solar radiation management. I don't know if Daniel has anything about things that could be done at the surface.
Yeah, I agree with Jerry. If you do things like that, it just gives you an excuse to keep being misbehaved and doing the wrong thing. And so you have choices. Like Jerry said, you need to decide whether you're going to make choices. And science in the last 20 years has given the world a lot of choices, but it always comes down to money at the end of the day. And I don't think any of us right now are still worried enough to really change our lifestyles. And it finally comes down to a question of cost continually. So it will cost a little more up front, but long term, I think as suggested in the question, is we should just start moving away as quickly as possible from a CO2-based fuel cycle or energy cycle.
Thank you very much. I have several questions that pertain to the overarching theme of this Wright colloquium about the sun. Questions that start in this way. If the sun does not create global warming, how do you explain the ice ages and the climate warming after them? And as a sort of follow-on to that, does your top-down plus bottom-up mechanism account for the warming between the Little Ice Age and the mid-20th century? And then perhaps another two questions related to the solar influence itself, do solar eruptions have an incidence on climate? And what is the maximum energy fluctuation related to the Milankovitch cycles?
Okay, those are all kind of related. I think the first thing is that the current thinking about what produced the ice ages were these orbital changes in Earth's tilt variations that were first identified and quantified by Milankovitch in the early 1900s. And you can explain a lot of what happens. Basically, one of the ways you can start an ice age, if the orbit becomes such that the winters become long and very cold and you get a lot of snow and ice that makes it through the summer, then you just start growing the ice sheet the following winter, you get more ice that makes it through the following summer, and you just start that kind of cycle, and everything starts cooling off. The planet starts getting brighter because you have more snow and ice. That's another way that you kind of get into it. The oceans become colder, they start sucking up CO2 from the air. There's less CO2 to trap heat. That's another way that the ice ages can kind of get going. So I think there is, at least at that level, we have some ideas about how the ice ages actually formed. What was the next? Oh, the Little Ice Age. So this is a really interesting thing. Little Ice Age is famous, especially in Europe, because of all the art that shows the glaciers, the valley glaciers coming down into the valleys and into towns and things. And they're very dramatic advance of glaciers. Little Ice Age, depending on who you talk to and what records you look at, may have lasted between 200 and 300 years. And it wasn't just one continuous cold spell. It was apparently episodic, and it wasn't cold everywhere. It was cold in various places at different times. The modern minimum occurred for about 50 or 60 years, kind of right in the middle of it. So the feeling is that the modern minimum, the lack of sunspots and the lower energy output from the sun during that time was a contributing factor, but there were also a lot more volcanic eruptions going on during that time period. And of course, as we know, as I've said, the volcanic eruptions put more reflecting material up into the stratosphere and produces a cooling effect on the climate. So I was thinking it was probably a combination of things that produced the Little Ice Age. It definitely wasn't orbital variations, because it was not on the time scale. The orbital variations are on thousands of years. The Little Ice Age just happened just in the 16 and 1700s. So it was these other factors involving solar output and volcanoes that we think produced the Little Ice Age. And I can't remember what the last tidbit was there. There was another.
What was the sort of range of energy fluctuations?
Okay, so just looking at the last ice age that was 22,000 years ago, the peak 22,000 years ago, it was on the order of a 20% decrease in the intensity of sunlight due to mainly changes of the tilt of the Earth's orbit between winter and summer. So that's on the order of 20%. Seasonal cycle is a factor of 5. Output from the sun with the sunspot cycle is less than 1%. So that gives you an idea of the relative magnitude of these forcings. So the ice age forcing is a big one.
Any other comment?
Oh, solar flares, something else, solar flares.
Yeah.
You want to say something about that? Or?
Would you repeat the question?
The question was, do solar flares influence things like extreme events, for example, in the climate system?
Well, that may be something you want to deal with in terms of
Well,
the effect
I'm
on
not
the
a
climate.
solar
I mean,
physicist.
but, I mean, solar flares have effects on things. They affect the particle stream coming toward the solar wind coming towards the Earth, and that has effects on the Earth's magnetic field. It has effects on ground currents and things of that nature, and you can get storm-like effects associated with solar flares. I'll turn it over to you in terms of the effects on climate associated with changes in magnetic field and so on.
I think what we see in the peaks of the 11-year sunspot cycle, you get more solar flares associated with when you have more sunspots. A lot of them are kind of right on the edges of the sunspots. You can see them when they kind of get on the edge of the sun. You can see these big flare things coming out. When you get a big flare, like Art said, you get this stream of charged particles that heads toward the Earth, and it disrupts the ionosphere, which then disrupts radio communications and all kinds of other things. And there's actually a center in Boulder that they monitor the sun, and if there's a big solar flare or solar eruption, they put out warnings, because you have a little bit of time before the particles actually get to the Earth, and they do this monitoring and warning system. It's called space weather. So they actually try to monitor what's going on the surface of the sun and how it may affect, especially communications on Earth.
Okay, I've got a few questions here that move away from the direct topic of this evening's conference on climate, but more related to solar physics per se. I think the first question Jerry actually answered during his talk, but it was if solar sunspots are so energy containing, why do we see them as being black? And then what kind of theories have tried to explain what causes the sunspots and their cycles? And is there any link between magnetic reversal on our planet and solar cycles?
Well, I'll answer the first two, and Art can do the second one. So these are exactly the questions I asked my solar physics colleagues when I got drawn into this problem. And I actually didn't go into this willingly, by the way. I only went into it when we could see these responses in our climate model that shouldn't have been there. And I was trying to figure out why this was happening, and that's how I get kind of drawn into this. But when I got into this, I was asking, and we have a solar physics group at NCAR, and I asked these guys, I said, well, these are spots, right? How come you get more solar output when there's these dark spots? And they go, well, it's not the spot, it's the faculae. The edges are brighter and have stronger magnetic fields, and they actually produce more energy that's even greater than the dark spot, which would obviously give you less energy coming out of it. So that was the answer they gave me to that. What produces them, I asked them that question too, and they said, well, we have ideas about what's producing the sunspots, but we don't know what's producing this 11-year cycle. And I said, you're kidding me. I mean, this has been observed since 400 BC, and you guys still don't know what's producing the 11-year sunspot cycle. They said, no, we don't. We have some theories, and the solar dynamo theory is a popular one that involves convection in the sun, and these things come up and they rotate around and they move towards the poles of the sun. And they actually have solar dynamo models. They're predictive models, and they were trying to predict the next sunspot cycle, and they were doing this in 2007, 2008 when we were writing these papers, and they were predicting the next solar max. And then we went into this prolonged solar minimum that lasted for 3 or 4 years that none of the models predicted. So it was back to the drawing board for the models. So they really don't, and so I thought, well, this is, I was wondering why this was the way it is. And they said, well, it's hard to observe things on the sun, and because we think a lot of what goes on that's important on the sun is happening beneath the surface, we have to infer what's going on because we can't shoot a probe in there, and we can't, we have to infer things. This is the kind of thing Art was talking about. We were looking at some of the charged particles that are coming out of the sun and trying to infer what's going on deep inside the sun. So I think that's one of the, solar physics is a really tough science because they're really observation limited. They're trying to look at things and try to infer what's going on in the depths of the sun to give them some idea of what may be going on. Maybe Art, you can say a little more about how you measure things from the sun.
Yeah, well, in terms of attempting to understand the sun in some detail, the central region of the sun, as I talked about Tuesday evening, is the area where the energy is being generated by and large. The majority of the nuclear power is being generated close to the center of the sun, and there's a radiative zone which extends out for more than 2/3 of the radius of the sun. And in that region, it's a relatively stable situation in which you have very dense material that's being heated by these nuclear reactions in the center. And as I spoke on Tuesday, we were able to observe those nuclear reactions using neutrinos that penetrate through this material and give us quite accurate indication that we understand which reactions are powering the sun and how much energy is being produced there. When you get close to the surface of the sun, you get into a convective zone. You get into a situation in which temperature differences result in the movement of material. And that's a much more chaotic type of situation. It is felt that the core of a sunspot is caused by a very intense magnetic flux. And there are theories that seem in general to be ways of understanding how you get very intense magnetic fields near the surface of the sun. This solar dynamo theory that was being discussed is simply the fact that there are different parts of the sun that are rotating at slightly different speeds. And so you end up with charged particles moving differentially as a result of these differences in rotation, and when you have charged particles moving, it can generate magnetic fields. On the other hand, what you saw today was the sorts of things that Jerry is attempting to do to model the Earth's atmosphere, and they're very complex, very major calculations, very extensive computer calculations and so on, in a situation which is a much more, let's say, less extreme situation, where you're dealing with air and the heating of air and the types of things that happen in the formation of clouds and so on, then extremely intense hot plasmas with magnetic fields in them producing what's happening near the core, near the surface of the sun. And so it is true that solar physicists, it's not an area that I work in, but they've been struggling for a long while to try to understand details of the chaotic behavior and also origins of the solar cycle. One of the ways in which they have been able to get more information about these outer regions of the sun is a technique which is also being used for the understanding of the central region, and that is what's called helioseismology. Seismology is used on Earth to try to understand earthquakes and how the Earth kind of resonates when you have a disturbance. They're doing that by studying the general movement of the surface of the sun and trying to determine, for example, how deep the convective zone is, how chaotic the convective zone is, etc. So it's a very complex topic, and it simply has not been successful so far to get a really viable theory there. So.
Thank you very much. A couple of questions on climate models. The first one is, how independent are the models that were used in the experiments that you showed to show the difference between climate being forced by natural forcing factors only and natural factors plus the anthropogenic effect? And then what other parameters besides CO2 are used in these models? For example, did you take into account land use changes, loss of forests, things like that?
Yeah, so the second question first, the answer is yes. We do take into account pretty much every constituent that we have measurements of that we know affect the climate system. So it's not only CO2, but it's also methane, other greenhouse gases. We can take into account ozone changes. We're getting models now that actually have atmospheric chemistry as part of the model, so it's calculating these various chemical reactions that produce and destroy ozone and other things. The top-down mechanism, those versions of the model had ozone chemistry in them. That was one of the first chemical reactions that was put in a climate model, was ozone chemistry. It was mainly put in to study the ozone hole, because that's still a very relevant topic. And that community, that was their first objective, was to try to get stratospheric ozone chemistry to study the ozone hole. But it turned out to have other benefits, looking at things like the reaction of the Earth's climate to solar variability. We put in land use changes. We put that in. Some models now have dynamical land cover, where the land cover can respond to climate. In other words, the plants can move around, slowly of course, but they can, if the precipitation regime changes, they can start growing in other areas. So you can look at changes in vegetation over time. So we try to account for as much as possible, but of course these are only tools. They're not totally complete. The limitation we have is computer time. One of the first applications of early computers in the 1950s was to produce a weather forecast with a very simple atmospheric model. And that's historically been one of the parts of science that's pushed or tried to take advantage of the limits of the available supercomputer power, because the faster and the bigger the supercomputer, the more detail you can include in the model. The more detail you include in the model, the more realistic it is, and the better a tool you have to look at things. We still, there's three aspects of this science, climate science, that have to happen simultaneously. One is good observations. So we need observations of the climate system, as many as we can get through the depth of the atmosphere, depth of the ocean, sea ice, land surface, everything else. One is understanding processes. This is just understanding what's going on out there and how this system works. And the other one is modeling it, being able to model it. And we use the models as these tools to try to help understand what's going on in the system. So all those three things have to happen to advance climate science. So we use these imperfect climate models that actually do a relatively good job kind of to a first order, but of course they still have limitations. But we use them kind of with all the limitations and take those into account and try to learn something about the system.
Okay, we're slowly coming to 8 p.m. Maybe just to close the session, a couple of questions which are more policy related. The first one is, well, in fact, both go in the same direction. If you want to guarantee a sort of upper limit to, say, 2 degrees beyond pre-industrial values, how much and how fast should CO2 emissions be cut?
Okay, that question relates to that last slide that I showed, where I showed the kind of the business as usual warming going up by 4 degrees by the end of the century, and the other one, the kind of the purple line that kind of leveled out. That leveled out line is a scenario which stabilizes warming at this kind of target that's been mentioned in the policy world to keep the warming less than 2 degrees centigrade above the pre-industrial value. We're already more than halfway there, so we don't have a whole lot of wiggle room there. But to get there, and there's a whole community of scientists that use things called integrated assessment models, and they are the group that actually produce these possible future scenarios. And their integrated assessment models have components. They have an economic component, they have a demographic component, they have an energy use component, a simple climate component, and they run these models and they kind of try to game the system. They say, okay, what if a population increased at a certain rate? What would the emissions of greenhouse gases be over the 21st century? Or what if economic activity did something and what would happen? So for them to get to that stabilized climate by the end of the century, they have to get, by 2075, you have to have negative emissions. And negative emissions of CO2 means you're pulling more CO2 out of the air than you're putting in. So that's a fairly significant challenge, as you can imagine, but you have to actually be pulling CO2 out of the air to bring the concentrations down and level them out. One of their rules they have when they form these scenarios that we use in our climate models, because we take the scenarios they produce and then we run them in the big global climate models to see what the climate effects are. But one of the rules that they have when they're producing these scenarios is you can't expect miracles. So they have to take existing technologies that we know about and apply them in certain ways to get certain outcomes. So there's already carbon capture, the CO2 capture and storage technology that exists. You can actually take CO2 out of smokestacks, and it's done to produce commercial CO2 actually for carbonation and other things. So we know that technology exists. The trick with that is where to put it once you capture it. And so there's ideas about where you can put it underground, but there's all kinds of issues with how that would work. But if you could apply that technology, you could actually do this. You could actually plant more trees. That's a kind of a typical one because trees pull CO2 out of the air. And who knows, there may be, by 2060, somebody at CERN may come up with a really great way to pull CO2 out of the air and really have a way to put these collectors out, and that would really help the problem. But we don't know, we can't count on that happening. So even with existing technologies, if applied in the right way, we could actually hit that target of negative emissions by 2075, but it would be very difficult, I would say, but it is possible.
So, a bit of optimism.
Yeah.
Thanks a lot, Jerry. Thanks to our panelists. I think we'll close this very interesting session for this evening. Thanks again to the audience. Je suis désolé pour toutes les personnes qui n'ont pas pu avoir leurs questions posées pour elles, mais c'est un peu les règles du jeu, malheureusement. Thank you very much. Merci beaucoup et bonne soirée.
I need a solar